In part B of the question, it wants us to calculate max speed after half a second. And so if you quickly look at this problem, you might think all you have to do is use the free body diagram for max while he's getting pushed, and just apply that for the full half second to find his speed after 0.5 seconds. However, that would not work in this case. And that's because there's actually two different types of motion in this problem, right? Remember, max is only being pushed for 0.1 seconds, right? So after 0.1 seconds, this applied force is going to go away. And so we have to take that into account into our problem. And so the way we're going to do that is by drawing our timeline to help us organize our information, right? We know from 0 seconds to 0.1 seconds, we have this situation where there's an applied force being applied to max, and he's going to be accelerating. He's going to be picking up speed. So we'll call this the speeding up interval. But then after 0.1 seconds, that applied force goes away. And so all there's going to be is this force of kinetic friction going in the opposite direction. So in this case, he's going to be slowing down until when the question wants us to figure out the answer, which is 0.5 seconds. Okay, so our ultimate goal is to figure out what is his velocity at this point, right? So what's his final velocity, v2? So in order to find a velocity, we're going to have to use kinematics, right? We can't use dynamics to directly solve a velocity. So let's think about what kinematic variables we have in this situation. We know our delta t, right? Our delta t is equal to 0.4 seconds, right? That's just going to be 0.5 minus 0.1. We can also find our acceleration using dynamics, right? Using our forces. For our second situation, when he's slowing down, the free body diagram is going to be similar to the one on the left. We're still going to have our force of gravity. We're still going to have our normal force. But now our applied force is going to go away. So we're not going to have this force. But our force of kinetic friction, since it's moving, is still going to be applied. So we can find our acceleration using dynamics. Now, seeing that this is a consecutive interval problem, the next most natural variable to find is the speed that he's starting with at the 0.1 seconds, right? And so then that way, if we find this v1, we'll be able to find what his with this acceleration. However, we also know that the velocity that he starts with in this interval is going to be the velocity that he ends with in this first interval, right? He's going to be speeding up, and then as soon as he starts slowing down, that velocity is going to be exactly the same. So we're going to have a final velocity on this side, which we'll be able to calculate. Again, an acceleration we'll be able to find using dynamics. We know our delta t is 0.1 seconds, and our last variable is going to be our initial velocity, right? We know that he's starting from rest, so his initial velocity is 0 meters per second. Okay, so then really our plan of attack, the way we're going to be able to solve this problem is 1, find the acceleration for our kinematics problem. Then step 2 is going to be use that acceleration along with the time and the velocity to calculate this final velocity. Then with this final velocity, we will know what the v1 of this interval is, right? That was the v1 of this interval. Our step 3 is going to be to calculate the acceleration of this interval using this dynamics. And then finally, our final step is going to be used to use this v1, which we calculated here, and our acceleration to find our final speed. All right, so let's start with step 1. Step 1, we're going to find the acceleration during this time period. So we know that our final step of this first piece is going to be using Fnet equals ma, right? This is the only way that we can find an acceleration using dynamics. So now we have to find our Fnet, and our net force acting on max is going to be equal to this applied force plus this force of kinetic friction plus this normal force plus the force of gravity. Again, our gravity and our normal force are going to cancel out because they're an equal and opposite. Our applied force from before is 285 newtons. So this is going to be 285 newtons. Again, let's say east is positive. And so we're going to subtract our force of friction, which is going to be mu k mg, right? And remember, that's because this is mu k Fn, and our Fn is equal to mg. So what we can do is write this as 285 minus 0.05 times his mass, which is 75, times 9.81. And this is equal to 36.7875. And so our net force is just going to be 285 minus 36.8. And we get 248 newtons, 248.2 newtons. And then, now we can use this equation. So our acceleration is going to be equal to F net divided by the mass, which is going to be equal to 248.2 divided by 75. And that's going to be equal to 3.31 meters per second squared east. All right, so now that we have our acceleration, we can move on to step 2. We can use kinematics to solve for our final velocity of this first interval. So we know that our acceleration is equal to 3.31 meters per second squared forward. We also know that our delta t is 0.1 seconds, and we know that our initial velocity is 0. Okay, so we want to use the kinematics equation that relates acceleration, delta t, v1, and v2. And so the equation we're going to use is acceleration is equal to v2 minus v1 divided by delta t. And so to rearrange this for our v2, all we're going to do is acceleration times delta t plus v1 is equal to v2. This is just equal to 0, this is v1, so what we're left with is v2 is equal to 331 times 0.1, which is going to be equal to 0.331 meters per second forwards. Okay, so now we've got our v2 for this first interval, and so that is equal to our v1 for our first interval. So we can write here that this is equal to 0.331 meters per second forward. And sorry, this shouldn't be squared. And actually I'll say east to be consistent. Okay, now we need to find our acceleration for the second interval. And so in the third step, again, we know that we're going to have to end up using Fnet equals ma, because that's the only way we can get an acceleration using a net force or using dynamics. And so the other way to find net force is by adding up all the forces acting on that object. And so we know that this is going to be equal to the force plus the force of gravity plus the force of kinetic friction, right? So it looks very similar to this, except now we only have well, we're not going to have an applied force. Okay, so our net force is going to be equal to our force of kinetic friction. But also, we know that the kinetic friction is not going to change between here and here, right? The mass is the same. It's on the same planet, so G is the same. The surface hasn't changed, so the coefficient of kinetic friction is exactly the same. So we can just use the number that we got back here, right? So our kinetic friction is going to be equal to minus 6.7875 newtons. And so now we can bring that back into our F net equals ma to Newton's second law. So our acceleration is going to be equal to F net divided by the mass. So that's going to be equal to minus 36.7875 divided by 75. And that is equal to minus 0.4905 meters per second squared east, right? So that means it's slowing down, which is what we were expecting. Okay, and so now what we're going to do is we have our acceleration, we have our velocity. So now the last step is just a kinematics problem again, right? So this is, let's round that to minus 0.49. So now that we have the acceleration, the initial velocity, and the time, we can figure out our second velocity using kinematics. So our final step, we know that the acceleration is equal to minus 0.49 meters per second squared east. We also know that our initial velocity is equal to 0.331 meters per second east. We also know that our time period is 0.4 seconds. And so all that we have to do to find our V2 is to use the following equation. V2 is equal to V1 plus a delta t. And so this is going to be equal to 0.331 plus negative 0.49 times 0.4. And we put that into our calculator, and we get a speed, a velocity, a second velocity of 0.135 meters per second east. And since it's looking for a speed, we don't need this direction. And so with significant figures, we're going to round this to 0.1 meters per second as his speed at 0.5 seconds.